back to our study of differentiation, or the derivative, in which, again, we're interested in the derivative as it gives us a tool to measure change. And again, change, we're always working with a function. The function measures real life, and we're interested in where things are going, or how fast are they changing. Are housing prices increasing or decreasing? At what rate are they increasing or decreasing? So these are common problems that come up, and the derivative is a tool to measure that change. When we define the derivative, we use this limiting process. We used a limiting process, and you probably thought we were going to be calculating limits for the rest of our time in calculus, and you would be incorrect. We define derivatives with the limit, and then we start to apply rules because we need to move a little faster. So today I will start to show you the easy way to calculate these, to calculate derivatives, and that'll become kind of the algebra that you have to be good at to solve calculus problems with regard to derivatives. So let's start on these formulas here. Here, the first one here, we got the derivative of a constant. What's the derivative of a constant? Well, I did that before when I had the derivative of, say, 2, but here's a constant. If I drew a constant function here, this is what? C. Okay? This is x. You know, f of x is equal to c. And you might see that, yeah, okay, what's the slope of that tangent line? It's 0. Yeah, okay, I can draw that one and convince you. How about x? Well, if I drew another function x, I can convince you. What's the derivative of x? I might convince you this is the function x, you know that. What's the slope of this function? What's the slope of the line y equal to x? Well, that's equal to 1. All right, the slope of x is equal to 1. Pretty simple there. What if I multiply, what if I put a different slope on my line? Cx. If now this function is, if I change this line, the slope of this line still goes through 0, sorry, this is Cx. What's the slope of that line? Well, that's just equal to C. That turns into a general principle here down in 4. If I take the derivative of some constant times a function, what do you think that's going to become? Well, if you multiply a function by a constant, you're just going to you scale the slope of that function. So this is just going to be C times f prime of x. I could write it this way. Right, remember my other notation? I could write it C dy dx. Assuming what? Well, that's assuming y is equal to a function of x. Okay, so here's, I'm again developing these formulas to make taking derivatives easier. You'll probably forget that the derivative is based on a limit, so we'll have to go back and remind you, but here's where we start making things happen. Okay, power rule, this is huge. Power rule, huge rule here. We're going to call it the power down rule. So derivative of x to the n. X to the n, any power n. N is now a, n is a constant. N could be 1, 2, 3, 5. So in this case, this is going to be n times x to the n minus 1. Okay, I just give you this formula. Now, you'll use this all the time if you want to see a proof. If you wanted to prove that the derivative of this function was that, what would you do? Well, you'd have to go back to the limit. And if you go to the Kahn website, he does do some proofs of some common functions. But for the most part, I will give you the result that you'll have to use. And we'll start working problems here. Okay, number 6 here. How about the derivative if I add f of x to g of x, or I subtract g of x from f of x? How's my derivative operator going to handle that? Well, basically it's a linear operator. So I'd say that's going to be the derivative of f of x with respect to x plus or minus the derivative of g of x with respect to x. So let's work an example in this case. Okay, so in this case, actually, here's my example right here. Here's my example, and I've got I want to take the derivative of function 5 times x to the 5th plus 7x to the 4th. I add these two functions, and I subtract the function x. That's supposed to be a squared term. Well, I'm going to use the power down rule here a lot. So I do the first thing. I guess I better do this slow the first time. That's going to be the derivative of 5x to the 5th dx plus, and as you can see, this is going to be the algebra of derivative calculus, and we will get very good at this and very quick. I'll try to remind myself to. Okay, so I break it down into 3 different derivatives. Well, what's the derivative of that? Well, that's going to be 5 times the derivative of x to the 5th dx. Okay, I'm working on this one. Let's do this again. And what's that going to be? It's going to be 5. 5 comes out. What's the derivative of x to the 5th? Well, the power rule. Here's where I'm using the power rule. I bring down a 5, x to the 4th. Plus, well, what about this one? Can I do this? Can I do, okay, I won't skip a step. That's going to be 7 times, I got to power down x to the 4th. Well, what's that going to be? This is a multiplier here, right? Multiplier 7 times 4 times x cubed minus, well, what about this? Minus, so what's the derivative of x squared? Minus x squared. Remember, that's going to be the power rule. That's going to be minus, oops. Get my pen back here. It's going to be minus 2x to the 1, right? We power it down, and we learned on the Kahn video, he derived this with limits. The derivative of x squared is 2x, so that's going to be minus 2x. Okay, so that would be my derivative. If I wanted to simplify that a bit, I'd say what? Well, that's going to be 25 x, sorry. It's 25x to the 4th plus 28x to the 3rd minus 2x. And that would be the derivative of that function. The product rule. Okay. Again, we're at the algebra that we got to get good at, and trust me, we will practice this. You'll get lots of practice. This is going to be, I use a little different note. Well, as derivative of g of x dx times f of x plus g of x times the derivative of f of x with respect to x. How might else I write that? I might write it like this because it's a little cumbersome. I might just call that g prime of x times f of x plus g of x f prime of x. Remember the notation, what the functional notation and how to read that. Okay, let's work an example. Here we're going to take a derivative of 2 functions here. The product of 2 functions. Well, this one is the first function, right? G of x. And here's the second function, f of x. You can see how we quickly start putting these rules together. The derivatives I'm following, what's the derivative of this first function? Well, let's do it. X to the 4th gets powered down, right? So power rule 4x to the 3rd. Plus, well, what's 5x? So that's 5. What's the derivative of a constant? That's 0. Okay. This is what? That's g prime of x. Okay, and I got to multiply that by what? F of x. What's f of x? So that's just x cubed plus 2x. Plus, okay, write down g of x. That's going to be what? Well, that's just x to the 4th plus 5x plus 1 times, that's g of x. What do I got to multiply that by? Oh, the derivative of that second one. What's that? Well, I got a power rule. What happens to x cubed? X cubed, we use the power rule. That's 3x squared plus 2x. The derivative of 2x is just 2. So that's really my answer right here. Do I want to simplify it at this moment? No, I don't. We'll work plenty of these problems, but again, what you'd want to do, you do need to simplify. You multiply all these out and get yourself an answer. Multiply it out and collect terms. But let me move on to the next rule, and again, in class we will work many more examples where we do simplify. Okay, last rule for a while here before the big chain rule. This is the quotient rule, which I guess is rule number 8 in case we're counting them, for not that you'd ever have to remember, oh, that was number 8. But the quotient rule, I've got a function divided by another function, okay? So I've got a ratio here, and what's that going to be? That's going to be the derivative of f of x with respect to x times the denominator, g of x, minus, okay, minus. So you got minus f of x times the derivative of g of x with respect to x. So it kind of looks like the product rule here, but notice the negative sign. Negative sign, and the derivative of g of x is second. And then we got to divide the whole thing by g of x squared. Once we learn the chain rule here, we could show you maybe you don't even need to know the quotient rule, but it's a handy little rule to know, not that complicated. Let's just apply it here. Okay, in this case, here's our example. Here's our example. I've got, what's my numerator function here? That's f of x. Okay, this is g of x. So I start off by taking, what's the derivative of f of x? Well, I power down x cubed, right? That's going to be 3x squared plus, what's the derivative of 1? Well, that's 0. Okay, I'll still put that in there for a while. Times g of x. Well, what's g of x? That's just x minus 1. Minus what's f of x? Okay, I put in f of x here. X cubed plus 1 times g of, what's the derivative of x of x? So that's just 1 minus 0, right? 1 minus, what's the derivative of 1? 0. Over what? G of x squared. What's g of x? X minus 1, so that's going to be x minus 1 squared. Now, maybe I will try to simplify this one to finish out the video. 3x cubed, I'm multiplying these two terms here, minus 3x squared minus, that's a squared term, I better not be sloppy there, minus x cubed minus 1. Keep that in parentheses here so I distribute that right, over x minus 1 squared. And that would be what? Collecting my terms, it looks like I'm going to have a 3x minus a 1. I'm going to get a 2x cubed minus 3x squared minus a minus 1, that's a plus 1, all over x minus 1 squared. What is that? That's this derivative. Okay? That's the derivative of this quotient function. Okay, so we've given you a lot of rules in order to make your life simpler to compute derivatives. Imagine if we went back to the limiting function to find out what the derivative of this last quotient was. So we got the product rule, the quotient rule, and the power rule being big things you'll use a lot.